Now the next basic element that we will consider will be a resistor. Okay, and as usual we define the voltage in some way. Okay, now I have chosen A to be positive and B to be negative, but you could easily do it the other way. But what is important is once you have chosen the sign of V, you should be looking at I going into the positive terminal. Okay, now this is the sign convention that's universally followed, so that's what you must use. And I think all of you are already familiar with the relationship between V and I for this particular element. V would be equal to I times R. Okay, and this is the famous Ohm's law, and we can also write I to be G times V. Okay, where this R is the resistance and this G is the conductance. Okay, if we plot I versus V for a resistor, what is the kind of plot that we are going to get? I would like some answers from participants on what is the plot that we will get if we plot I versus V for a resistor. Yes, I can.
Sir, I had a question of
Okay, I'm not able to hear the question. First of all, somebody commented that there is no video. Because of bandwidth constraints for some users, I am now not sharing my video. I am only sharing the board on which I am writing. And many people answered this question as well. The answer is pretty obvious. It is a straight line passing through the origin. And the slope of this would be G, the conductance G. Okay. Is there a problem with the audio?
Can you hear me, sir? Hello?
Yes, I can hear you.
Hello? Question.
What is the question?
You were about the parts of the antenna. Now, hello?
Oh, okay, let's deal with that later. Okay.
All right.
Okay. Okay, some people said there is no audio. If this is the case, please type it in the chat window. And I have disabled the video because some people had a very low bandwidth, and with the camera on, it was taking a lot of their bandwidth. But if there is no audio, if you are not able to hear me, then please type it into this. Okay, it appears that the audio is fine. So the I versus V characteristic for a resistor would be a straight line passing through the origin, and that's quite important, and the slope of that would be G. Okay. Now let's quickly look at how a resistor is made. This is not the main focus of the course, but this you can think of as some general knowledge. The easiest way to imagine a resistor that is made, although it may not actually be made this way, is to have a slab of some material and you can have contact at this end and the other end. Okay, and this will serve as the terminals to which you can apply either the voltage or the current. Okay, so you can apply a voltage here and you can measure the current there, and with, as we said earlier, V would be related to I by this relationship. Okay, so now what happens in a resistor is that electrons will be accelerated by the field created by the voltage applied between the two, but of course it's not moving in a vacuum, so it will accelerate a little, it will collide with some fixed charges in the lattice of the material, then it will start accelerating again, and so on. And depending on that material, it will acquire a certain average speed, and that will give you a certain average current. Okay, so you need the knowledge of electromagnetics and materials to calculate the resistance for a given material. Okay, but we will not go into those issues. We will take the resistance value for granted. Okay, and then use that. Now for a slab of this type, let's say this dimension is W and this dimension is L, and the thickness of this is T. I think many of you already know that the resistance R will be the resistivity rho times the width of the material times thickness, that is the cross section area across which the current is flowing, the area of that, divided by the length, that is the length along which the voltage drop is measured. Okay, so this is the formula for the resistance, and it is quite simple for a slab like this, but the resistance itself could be made in any number of ways. You could have resistance which is coiled into a spiral and so on. In those cases, the formula will be complicated, but what is important for us is the relationship between I and V, and it will always be simple like this. Okay, we will not worry about how to calculate the resistance for a given physical structure, but we will take the resistance as granted and we will use this model. We will use what is given here, V equals IR or I equals GV, and sometimes we will use this graph. Okay. Now there is some comment in the chat window. Somebody said that it's a straight line passing through the origin with 45-degree slope. Okay. Now here you have to understand that the x-axis and y-axis have different dimensions. So measuring the slope as 45 degrees has no meaning. Okay. That will be meaningful only if they have the same dimensions. Then you can say the slope is unity. In this case, the slope is in conductance, which has some dimensions. Okay. So as you know, the resistance is measured in ohms with this symbol, and the conductance is measured in Siemens, and we use the symbol S. Okay. So that's the definition of a resistor. Okay. That is, once we define the relationship between the voltage across the resistor and current through the resistor, our job is done. We have described the resistor. So what does a resistor do? If I connect a voltage source and a resistance like this, it's pretty obvious that the voltage across the resistor equals the voltage applied by the voltage source. Okay. So this is V0 and V0 is applied across the resistor. Actually, this is a very trivial application of Kirchhoff's voltage law. If you count the drop from here to there and there to there in the resistor, the sum will be equal to 0. Okay. So under these conditions, V will be equal to V0. This is by KVL, and this is so obvious that we don't think of it as application of Kirchhoff's voltage law, but that's what we are doing here. Okay. Now, because voltage V0 is applied across the resistor, a current I, which is V by R, which is V0 divided by R, will flow through the resistor. Okay. And that of course has to come from the voltage source. So the voltage source will supply a current of V0 by R. Okay. Now, whether you apply a voltage or apply a current, the resistor behaves in the same way. You can think of it as the current generated by an applied voltage or a voltage generated by an applied current. So I could also do this. Let's say I equals I0, that is, what this is saying is this will maintain a current flowing from top to bottom equal to I0 through the current source. So that means that the current flowing here will be equal to I0. This again is a trivial application of Kirchhoff's current law. The current entering this node here equals the current leaving that. That is, the current supplied by the current source equals the current flowing in the resistor. Okay. And in this case, the voltage across the resistor, it has to be measured like this because the current is flowing downwards through the resistor, and that will be equal to I times R, which is I0 times R. Okay. So there is a question from Subhashish. Please go ahead. Subhashish, go ahead. Okay, it appears that he has dropped off. Now, so I think all of you would already be familiar with these cases. That is, if the voltage is applied across the resistor, we'll have a current V0 by R flowing through it. Or if my current is applied, current source is connected to a resistor, current I0 will flow through it. In this case, you will get a voltage drop of I0 R, and in this case, you will get a current of V0 by R. Okay. Now, this comes from very trivial applications of KVL and KCL. I am not going to describe that. If you want to, you let me know and I will do that. But it's pretty obvious that the same current is flowing in the voltage source and the resistor here, and in the current source and the resistor on the right hand side. Okay. Now, one of